Okay, everyone. So now it's time for the actual Krebs cycle, easy and clear, or the citric acid cycle. So as we did in the previous videos, to go over aerobic metabolism, which means when oxygen is present, we had glycolysis, then we did the transition stage, and now we are on to the Krebs, the big one, the one that everybody refers to in this metabolism process is the Krebs cycle. Now, in metabolism, we have glycolysis no matter what. But if there is no oxygen present, then it goes over to anaerobic metabolism if there's no oxygen present. But in the presence of oxygen, it comes over here to the right, and we do the steps for aerobic metabolism, also called cellular respiration. And those steps are after glycolysis, we have the transition step, we have the Krebs cycle, and the electron transport chain. So we are on the Krebs cycle right now. Now we know in glycolysis, we went over that glycolysis brings the glucose in through the cell membrane and into the cytoplasm of the cell. And then the transition stage brings it through the mitochondrial membrane to enter the mitochondrial matrix. And now we're in the Krebs cycle, which occurs inside the mitochondrial matrix. So here's a picture of that of a cell, and inside of the cell is the mitochondria, which is an organelle. And the Krebs cycle happens inside the mitochondria in the mitochondrial matrix. Remember, there are two molecules because in glycolysis, we divided up the glucose molecule into two smaller halvesies molecules. And so we want to make sure we continue with keeping track of all of the inputs and outputs, but we have to take everything we do times two because the cycle is to both molecules that are originally created from that one glucose molecule way back in glycolysis. Also, it happens in the mitochondrial matrix, which is what I just showed with this drawing. And it is the middle step in aerobic respiration when you have oxygen available. Because remember, if there's no oxygen, we can't do the transition step. It has to go over to fermentation. So as long as there was oxygen present to do the transition step, we are in aerobic respiration, and the next step will be this Krebs cycle. And the Krebs cycle is also called the citric acid cycle, or TCA, the tricarboxylic acid cycle. This is all the exact same thing for the Krebs cycle. They're the same thing. So if your teacher or your textbook uses one of these other terms for it, we're talking about the exact same thing as the Krebs. So don't worry about that. Don't get confused. Now, the Krebs is definitely a cycle because the beginning is the acetyl-CoA we got from the transition stage. From the transition stage. And it fuses with the end result of the same Krebs cycle. So this end result of the previous Krebs cycle being processed is oxaloacetate. You take that and it fuses with the acetyl-CoA, which was the end product from the transition stage, and you put them together and you get citrate. And so citrate starts out the cycle, but then it goes and processes in this big circle, and you end up with this same end product, oxaloacetate, which then again goes into the next Krebs cycle, fuses with acetyl-CoA to give us more citrate, and then that starts another cycle of the Krebs cycle. So you can see how this is cyclical and happens in cycles just over and over and over again and again and again. So a good mnemonic to memorize these products along the steps of the Krebs cycle is citrate is Krebs starting substrate for making oxaloacetate. And a substrate is just the other ingredient that's used in the recipe for making something. So, I mean, it has a more technical definition than that, obviously, but pretty much for layman's terms, you can just consider the substrate or the substrates are the ingredients, and the substrate is sort of like the minor ingredient that is applied to the major ingredient in order to make a new thing. So that's the substrate. So as you can see, this starts out with the oxaloacetate and the acetyl-CoA fusing together and starts us off with the first product of citrate. So citrate, C, and then we go to isocitrate, which starts with I. So it's called isocitrate instead of citrate, just because there was a rearrangement of the atoms in the molecule, so it's shaped a little bit differently, but it's still kind of the same thing. So that's called an isomer, which is where the iso comes from, an isocitrate. So citrate is citrate isocitrate. Krebs's, so that's going to be alpha ketoglutarate. So this little symbol right here just means alpha. It's like kind of a flattened cursive letter A. So in cursive A, you would do that, but this is kind of a just you're writing A, but you're in a really big hurry. So that's alpha. So we would just call this alpha ketoglutarate. And then the next thing is succinyl-CoA, coenzyme A, and we remember coenzyme A from the transition period, transitory stage. So that's citrate is Krebs's starting, and then substrate for succinate, and 4 would make the substance fumarate, Making is the substance malate, and then oxaloacetate, which is the mnemonic for oxaloacetate. It's not really an abbreviation. So citrate is Krebs's starting substrate for making oxaloacetate. And that's how you can remember these uh, intermediary products that we're making as we go around the circle, as we go around the cycle. So here is the diagram. And don't worry if this is too much and a lot of really overwhelming for you. We're going to go through this step by step in this video. I'm going to try to not take up too much of your time, but I'm going to go through every single individual step in this. And then we're going to come back to this diagram so you can clearly put it all together and see how it all works. After we go through this step by step, then you should be able to come back to this diagram and it should make a lot more sense to you. Now in this diagram, the purple are the enzymes used. So purple are the enzymes used for each step. And then we have the products and the input. The input and the outputs are in green. And then the actual Krebs cycle intermediary products are in orange, or in the orange highlight. And then we have the carbon chains drawn out in orange for you. Okay, so the first step to the Krebs cycle is you take the end product from the transition stage that we did in the previous video, which is acetyl-CoA, which are these a 2-carbon chain plus this coenzyme A added onto it. And then you fuse that together with the Krebs cycle's end product, which is called oxaloacetate. And the oxaloacetate is this 4-carbon chain. And you end up getting, well, a 2-carbon chain plus a 4-carbon chain ends up giving you a 6-carbon chain. We've taken off the coenzyme A now, and this is called citrate. And the enzyme that is used to do this, to make citrate, to synthesize, which just means to make, to synthesize citrate is citrate synthase. See, synthase is the ACE is because it's an enzyme, because enzymes all end in ACE, and you're synthesizing citrates, you're making citrate, so synthase. Citrate synthase is the enzyme to synthesize citrate. So see, if you want to synthesize citrate, you need the enzyme citrate synthase. For step 2, now we have citrate that we made in the previous step, which is the 6-carbon chain, and we're going to turn citrate into isocitrate. And isocitrate is named that because it's still citrate, but it's an isomer of citrate, which just means a rearrangement of the atoms in citrate. So we're still dealing with the same atoms and the same molecule, but it's just rearranged. It's rearranged from citrate. And so we're going to call that isocitrate because it's a rearrangement or an isomer of citrate. And of course, this is still going to have a 6-carbon chain to it because nothing's been added or subtracted. It's just been rearranged. And the enzyme used for this is aconitase. Now, step 3, now we have isocitrate from the previous step, step 2, and it's decarboxylated. So what does decarboxylated mean? It means it's lost a carbon. This DE means something's been removed. So it's been decarboxylated. So it takes away CO2, which takes that extra C, that 6th C of the isocitrate, and it turns it into a 5-carbon chain. So 1, 2, 3, 4, 5. Now we have a 5-carbon chain. And the enzyme used for this to make to turn isocitrate into ketoglutarate is isocitrate dehydrogenase, because the dehydrogenase indicates that it is decarboxylated, or it has had a carbon taken off of the chain. So we're 1 carbon short now. We have 1, 2, 3, 4, 5 carbons in this chain for alpha ketoglutarate. Now step 4 is we take that alpha ketoglutarate we just made from the previous step, and that again is decarboxylated, lost another carbon, and so we lose this 5th carbon at the end of the carbon chain, and now we add coenzyme A to it again. And so now we have a 4-carbon chain with a coenzyme A added at the end, which is called succinyl-CoA. That CoA is short for coenzyme A. So this is called succinyl-CoA. When we take ketoglutarate, remove 1 carbon, and add a coenzyme A to it, so now it's succinyl coenzyme A. And the enzyme for this is alpha ketoglutarate dehydrogenase, because the dehydrogenase, anything ending in dehydrogenase, is what causes the decarboxylation. Ooh, that's a hard word to pronounce. Okay, so step 5 is we take that succinyl coenzyme A that we made from the previous step, and it loses its coenzyme A. So we have this 4-carbon chain with a coenzyme A on it. We remove the coenzyme A, and it turns into succinate, which is just the 4-carbon chain without the coenzyme A on it. And the enzyme we use for this is succinyl coenzyme A synthetase because you are synthesizing succinate. Now, step 6 is that we take that succinate and we turn it into fumarate, or fumate, sometimes it's called. And these are both 4-carbon chains, if you notice. Succinate and fumarate are both 4-carbon chains, and the FAD takes 2 hydrogen ions away, which turns the FAD into FADH2. So it's still going to look the same. This drawing of the 4-carbon chain is still going to be a 4-carbon chain, but the other things that have been coming off of the carbons, the hydrogens, that number has changed. And the enzyme used for this is succinate dehydrogenase. Now, step 7, now that we have the fumarate, we're going to turn that into malate. And again, this is still 4 carbons, and this is 4 carbons. And so this is just an input of water, of H2O, gets input into fumarate and the enzyme fumarase, because we're taking fumarate and we're taking the enzyme for it. So the ACE means the enzyme. And that's going to turn it into malate. Now that we have malate, which is the 4-carbon chain, we're going to turn it into another 4-carbon chain called oxaloacetate. And this is the final result, or the final product of the Krebs cycle. And we're going to take this oxaloacetate, and it starts the cycle all over again, where this oxaloacetate combines with the acetyl-CoA from the transition stage and starts the cycle all over again. And the enzyme used for this is malate dehydrogenase. So that is what this entire cycle is all about. That is it. It's really just as simplistic as that. I know at first glance, if you have not gotten used to reading these diagrams yet, this might seem overwhelming at first, but just take a look at what we're doing here. We have the acetyl-CoA. We start with the acetyl-CoA, and we take the enzyme citrate synthase to synthesize the citrate that we're going to make out of it. And we have to combine that acetyl-CoA with the previous Krebs cycle product, the end product, which is oxaloacetate. With the enzyme citrate synthase, it makes citrate. And then with the enzyme aconitase, with that citrate, that's going to rearrange a couple of things into isocitrate. And then we take that isocitrate, we add an oxygen, and it gives off a carbon dioxide. We add the NAD+, which removes a negative hydrogen anion and gives us NADH. And that all combined makes alpha-ketoglutarate, which is a 5-carbon chain, because see, we've removed a carbon because of the CO2. So that means we're taking off this end carbon right here, which gives us 1, 2, 3, 4, 5 left, which is the alpha-ketoglutarate. Then we have the alpha-ketoglutarate. We input some more oxygen and some more carbon dioxide is given off, which takes away this 5th carbon on the chain. And that gives us succinyl coenzyme A, which is the 4-carbon chain that we see here. The succinyl coenzyme A uses the enzyme succinyl-CoA dehydrogenase, and it removes that coenzyme A. And also we have ADP swooping in and taking up a phosphate group, so that gives us ATP. And altogether that creates the new product, intermediary product, succinate, which is another 4-carbon molecule. We take that succinate 4-carbon molecule, the enzyme is succinate dehydrogenase, and we take another energy carrier, which we haven't talked about yet, which is FAD. And FAD removes 2 hydrogens to give us FADH2. And all of that total generates the next intermediary product called fumate, which is another 4-carbon molecule. We take that fumate, we input some water and the enzyme fumarase, and that's going to give us malate. So the amount of carbons don't change. It's still a 4-carbon molecule, but now it has some water attached to it. And then we take that malate, and the NAD positive swoops in, removes a negative hydrogen ion, giving us NADH. With the enzyme malate dehydrogenase comes in, and altogether that gives us the end product, another 4-carbon molecule, oxaloacetate. And then that goes back into the beginning of the cycle with acetyl-CoA from the transition stage, and it makes citrate, and we start all over again. So what are the end products here for the Krebs cycle? By the end of the Krebs cycle, we will have amassed 2 ATPs, 6 NADHs, 2 FADH2s, and 4 carbon dioxides. And this is including both molecules. Remember I said you have to take everything times 2? So this is including taking everything times 2 for both molecules that was divided back in glycolysis. So that is it for the Krebs cycle. If any of this went too fast for you or didn't make sense, please feel free to leave a comment and ask a question, and I will get back to you as soon as possible. Or you can also go to my website where I'm going to post a free PDF download of all these notes from this entire series, and you can actually email me from there as well.